Hello, everyone. My name is Nick Fenter. I'd like to welcome you to today's webinar, The 3 Ingredients for Robust Geologic Models, Thought, Culture, and Tech. Our presenter today is Desiree Winkland. Desiree is a geologist with our sales team, and she provides solutions to the mining industry here in the North American region. So just quickly, a few things before we get started. First, today's webinar will conclude with questions and answer session. So please feel free to write your question in the question panel on the right hand. You'll see that on the side of the screen in that little panel. And also, you will receive a link to the recording of this webinar by email. So in case you'd like to see it again, it will be available on the website as well. So you're definitely not going to miss it today. I'll now hand you over to Desiree.
Well, thanks, Nick. As Nick said, I am a geologist who works in sales, but I've also spent a lot of my career working in the consulting and teaching arena, specifically with companies to help figure out modeling best practices. And during those sessions, I'm typically asked 4 main things. Why is my model so ugly? I can't get it to look the way I want. Why does this model take so long? How come my model isn't reconciling? I just want to go back to being a geologist. I'm tired of being in front of the computer. I want to go back out in the field. And I'm sure a lot of you can relate to that. And if you want, you can take a quick moment here to chat in what your top frustration is with modeling. I know these have come up for me personally as well as in my training sessions. So with these issues, most of the answers to those 4 main questions stem from a disconnect between 3 main things in my experience, which is first, a company's culture, the geologist's mindset, and the technology that they're choosing to apply. When all 3 of these things aren't working together, I waste time trying to build models that are subpar, and then I burn out because I'm not really doing what I love, and I don't really feel like what I'm doing matters to the rest of the industry that is looking at the models I'm producing. And so you may be thinking, well, culture is kind of difficult to control where I work, which is totally true, but we can influence how culture affects our models through how we use our geologic thought and the technology we apply to those models. So we'll take a few moments to kind of review some of those things. So let's start off with mindset. The first concept that I talk to people about is, what is a model? Where do they come from? Why do they matter? And these may seem like simplistic concepts, but realistically, even though I learned a lot of this stuff in school, once I got into the pressure of the workforce and trying to get models out quickly to anybody who needed them, I kind of forgot the importance of keeping these in the foundational concept while I'm modeling. So let's quickly review that. What a model is, and this is one of my favorite quotes of all time from one of my coworkers, which is, all models are wrong. It's just some are more wrong than others. So basically what this is saying is there are no perfect or perfectly correct geologic models. They are either well-informed and beneficial or useful. So with modeling, our goal for a robust model is to produce a well-informed, useful model based on the best available information, realizing that it will change, and it should change. So models come from our sampling data out in the field, drilling, previous research, and that sort of thing. But as we go through our scientific method that we learned in school as geologists, which is make observations and collect data, explain those with a model, that's where we go ahead and we build those models. In my personal career, I would usually stop at this point and hand it off to someone who will look at the model, forgetting that, oh wait, I should probably go through a peer review process with my coworkers, making sure that what I produced actually makes sense geologically, testing that hypothesis I've put together, and then refine it. And so a model is more than just producing a wireframe or a block model. It's really a cog in the scientific process that allows us to ensure that we are thinking geologically in every aspect of the data science that we do. So why does a model really matter? Well, geology is the foundation principles for everything that flows from it in a mining environment. So our geologic model gets put into a resource model, which gets handed off to the engineers to produce mine plans and schedules, which then get passed off to the rest of the general manager to put together the economics and the business model. So realistically, the geologic model is the foundation for decision making that flows throughout the entire mining cycle. And I love this quote that Mark Bristow said last year, which is successful gold mining starts with a ore body quality. And you can't understand if an ore body is of a quality nature if we don't understand the geology that took place to deposit it in the first place and test those hypotheses that we put together. So now that we've taken the time to kind of review what is a model, why do we follow a scientific process, and why do we need to test our hypothesis and how it goes through, that should hopefully put us in a good frame of mind to move into the technology piece of modeling. And like you guys, when I entered the industry, maybe later or before you, I was used to doing most of my models in paper sections. So when all these technologies were introduced to me in industry, like explicit modeling, stratigraphic modeling, unfold your model, kriging, implicit modeling, sculpting, machine learning. All these things were so exciting that I was like, oh, I can't wait to put my thesis data in the computer, see what it really looks like in 3 dimensions. Oh, I wonder how that would be. Well, the problem is I just took a tool and tried to throw my thesis data at it without thinking about things like, how much data do I really have? What am I going to be using this model for, and how complex is the geology that I'm modeling? And the reason why this matters is that the tools that are available to the industry are based on mathematics, meaning things like, for example, stratigraphic modeling, which we typically think of as for coal deposits only, were mathematically designed to help interpolate geology across lowly dipping, widely spaced continuous deposits, because that's typically what we think of with coal and how they're deposited. But stratigraphic tools are a mathematical purpose for that fit. And so I can't apply a stratigraphic technique to something that is reverse faulted because the math can't handle a duplicate Z value, for example. Or implicit modeling, like in the example of my thesis data. I was so excited to try to throw in my thesis data when I entered industry into implicit modeling techniques, not realizing that radial basis function in most of the software platforms are a radial function, meaning it'll create nice little balloons or blebs in areas that I didn't expect because I didn't really have enough drilling to constrain the model for what I knew was actually occurring geologically in that deposit. So picking the right tool for the right job will save you time and give you something that will be illuminating and more robust, because you're not trying to force a mathematical overprint for the data you have. So I like to balance what I'm going to use my model for, how much data I have and how continuous it is, with the geologic complexity to help me pick which tool will work. So when I first start modeling, I like to review 3 things. Biggest thing, my data. How much do I have? Is it evenly distributed? Where is that data coming from? Is it in paper maps, digital maps? Do I have drilling? Do I have channel sampling or geophysical data? And how much of it is valid? What can I trust? Because if I use all the data at my disposal, I might be able to get a really good model, but if something doesn't line up appropriately with what I know should, or what I'm assuming should be happening in the field, I can say, okay, oh wait, that came from a historical drill hole 20 years ago. Do I trust that source, yes or no? And if I do, what am I assuming that's incorrect? So it gives us a really good check as far as what is going on geologically to make sure that we are really testing our hypothesis before we go ahead and model. Next, I like to look at what the purpose of my model is, because I could be looking at data to try to visualize the deposit, have good conversations with my fellow geologists, and do a peer review on what we think is occurring in a deposit for future exploration drill planning. In that regard, I might not need detailed information at a small scale, but more at a regional scale. So that'll impact which tool that I'm going to use and how much time I'll be putting toward that finite information that I can review. Or if I'm doing grade control, that's at a smaller scale because I'm usually looking at what I'm going to be mining for that week or that month. So I'm looking at a smaller area in more detail, and that'll help me refine how much data I can apply to the technique that I'm going to pick. Or, for example, if you're having to do a life of mine, this is probably one of the biggest lessons that I learned in modeling and having a good mindset before I start modeling, is that if I am handing off my block model to an engineer for mid-range planning, the scale that I create that model at needs to be consistent with how it's going to be mined. Because if I'm creating a model that is crazy detailed, it might be a great geologic model, but I'm spending too much time putting that detail in my model when the engineer is going to regularize those blocks into a mining unit that makes sense for how it's going to be mined anyway. And that data is lost, essentially. So keeping in mind how your model is going to be used, how much data you have, how valid it is, will really help you hone in on which technology piece should be applied or could be applied to help you ultimately save time. Now that we've kind of looked at data, the last thing I look at is geometric shape. So earlier when I mentioned geologic complexity, I'm not necessarily talking about geologic paragenesis or alteration overprinting, but realistically the geometric relationships within the geology complexity is what we're trying to understand. Because remember, the technology tools out there are based heavily on mathematical algorithms, so that geometric interaction will be boiled down to 4 main geometries. And this is based on my coworkers and I's past experience. And so the first one to consider is 1, horizontal geologic shapes. Is it vertical? Is it folded? Or is it amorphous? So the next section, I'm going to go through these 4 geologic shapes in relationship to the data we have and the purpose of the model. And I'm going to be showing some simplistic examples of these to really illustrate the point of keeping in mind your geologic thought and your technology for modeling. However, we have, or I've personally used these scaled up for complex interactions. So these types of tools will work depending or regardless of the complexity in your deposit. So first off, horizontal. The next illustration we're going to be modeling is going to be a country rock example. However, other examples of horizontal geologic features that have worked with this modeling technique are things like coal, or parts of a volcanic massive sulfide, or parts of Carlin or sills. And the biggest thing that you want to consider is how much data you have and how evenly spaced it is. With near horizontal techniques, tools like stratigraphic modeling that I mentioned before will work wonderfully when modeling sills, because you're not at steep dipping deposits. The data is relatively evenly spaced out. And in this example, I'm using it predominantly for visualization, understanding what's going on so I can go back out into the field, do some additional surface mapping, and potentially some drill hole planning when things get approved budget-wise. So with that, here's a quick example of utilizing stratigraphic techniques. And the neat thing about stratigraphic is that it can take a lot of your surface data, so things like knowing where your structural faults are that you've mapped regionally, and any drilling that you have, and it will produce fault blocks for you. And that's a really great time saver when it comes to modeling lower level, nearly continuous deposits, because the faulting and the structure is really important for understanding depositional environment and where you could potentially want to explore in the future. So here's a quick section of that same deposit in a cross-sectional view. So again, you can see how it's not perfectly flat for utilizing a stratigraphic modeling method, but you get the fault blocks with less effort than having to model each individually, flag them in a block model, and cut them all up. So that's a good time saver. Next is narrow vein, again with vertical geometric shapes. These could be veins, dikes, faults, different things like this. And there are a lot of great narrow vein modelers out there, whether you look at one in Vulkan or Leapfrog. There's some in Miro Geoscience as well. But basically, it takes a lot of the same stratigraphic techniques and rotates them, or uses a radial basis function and models the hanging wall and footwall, and then you can put those together into a solid, or it'll automatically do that for you. Again, you want to look at how much data you have. With narrow vein, it may or may not be evenly spaced. This example, it's not. However, there were underground workings that we were able to incorporate into our map data with interpretive sections. And again, this is mostly being used for visualization and exploration. And you may notice in this section, this is the exact same data. So I want to point out that even though I'm modeling a deposit and I'm trying to understand what's happening on a global scale for the deposit, I'm using one method for the country rock, which was stratigraphic, because it worked really well based on the geometry I'm modeling. And then I was able to model the mineralization occurring using a narrow vein feature. Now, you can go through and ask yourself questions, okay, well, is this enlightening? Visually, yeah, I'm seeing faults on the surface, and I'm also seeing veins that are loosely related to them, but not necessarily with them. Okay, that gives me time to go and test my geologic assumptions, talk to my coworkers and be like, hey, could there be other structures impacting the depositional environment of these veins? What else are we missing? Let's go back and investigate. And that's really the purpose of a model, is understanding what could be occurring, how we can test it, and go back and refine our model. The next example is one that was super exciting because it's an active mining environment with a lot of drilling, over 1,000 drill holes. There's historical and updated drilling. It's evenly spaced. So even though this example is a folded deposit, it is coal. And this could potentially work for other things like roll front uranium, large scale soft sediment deformation, metamorphic, those types of things. And this model, its purpose is more for drill hole planning, understanding what's happening on a regional scale, as well as being able to pass things off to the planning department, meaning they need a block model. One of the quickest ways to get to a good geologic block model with a lot of data is machine learning. And so that we threw this one into Domain MCF, which is an artificial intelligence machine learning program, which takes all the data available to it, trains a model, and then spits out the best example. And the great thing about machine learning is it runs through the same scientific process that we talked about before: gathering data, creating a model, testing that model, refining that model. It just does it hundreds of times, so that way you get a really good result quickly that you can run out into the field and do some more legwork on. And what I loved about this is, even though in the model it used the geology and the grade to pull out the block model, it also put in those fault block information as it did the model to help train it, and it pulled that information out automatically, almost similar to the first example I mentioned where the fault blocks are important. It just, the model happened to find that information for us, and then we were able to go out and test it. So the last geometry that we have is amorphous, and in this example we're looking at a copper. Basically, amorphous is anything that doesn't easily fit into the previous three shapes. So in this example, we're looking at greater than 100 drill holes. There's relatively evenly spaced data, approximately 50 feet apart. We do have interpretive sections, but not any geologic triangulations yet. And the main purpose of this is visualization and actually grade control. So in this next example, we had originally created the shape using implicit modeling, but with the updated drilling and the production information, we used something called sculpting or a morphing tool, which allowed us to quickly go through and adjust based on the intercepts in the drill hole. And then we could say, okay, is this realistic? Is it not realistic? And gave us the resolution that we needed to get the volumetrics out for reconciliation and production geology. So in review, culture is definitely a driving force to the success of a robust model. And breaking down those silos between the geologist and the grade control engineer and the planning engineers to really understand how a model is going to be used at your site will allow you to really test your models and train your own assumptions to make sure that the model you're creating is really useful. And while culture is difficult to change, it can change over time through influence. So don't get bogged down in the pressure to chase ore if you can help it. I know that's a hard one. But geology really does matter to everyone, which is a really good takeaway to remember. And next, in mindset, make sure that you think about your geology. Don't overcomplicate the situation and look at the big picture, not just how your model fits to your own geologic understanding, but into the greater good of the ecosystem that your model will be used for. And don't be afraid to challenge your own assumptions. Test your model. I know sometimes it's hard. I've done it myself where I feel like I know a deposit better than anybody else, but there's some really, really great enlightening events that happen when we take the time to listen to each other and test our own assumptions when we go ahead and model. And lastly, technology is a tool, and picking the right tool for the right job based on the data that you have, the purpose of the model, and the complexity that you're trying to model tool to will save you time. And don't feel like you have to use the same tool for everything that you're modeling. You can do a lot with interacting geologic complexities with faults and sills in one method, and your country rock in another, and your mineralization in another, and then through geologic superposition, you can overprint all those things together in subblocked block models and so forth. There's great tools out there for that. So again, pick the right tool based on geometry, model purpose, and data density. So with that, I'll hand it back over to Nick for some additional questions.
Thank you, Des. It was very enlightening. Are you ready for the questions?
I am ready.
Awesome. Okay. So we've got the first question here is, if you have multiple geologic shapes, how would I put the models together cohesively?
So kind of like I mentioned on that last slide, one of the biggest things that I've encountered in my consulting career is that I've gotten hung up trying to put them into wireframes, when in reality, the use of that model will be going to planning or for miniature grade control models, which need to be in block model format anyway. So regardless of if you're using Vulkan or Leapfrog or GemCom or whatever, there's a lot of geologic superposition that you can put into that model. So I can put in the country rock first in my blocks and then overprint the veins on top of that. And so that way you can put together all the information from different sources into one cohesive visualization tool.
Awesome. And then another question here that we have is, what happens if you don't have one of those three ingredients to make a robust model?
So realistically, as geologists or as humans in general, we have the ability to control our own selves. So in my experience, when I felt like I didn't have the right mindset, it took someone reminding me, hey, have you taken the time to think about this geologically? Stop just trying to use a mathematical tool to get it to match your drill hole intercepts. Does this make sense? And then I can take the time to stop and re-educate myself on, okay, what is known about Carlin deposits? What is known about this modeling tool that I maybe didn't know about before? Taking the time to get yourself in the right mindset is something that you can control. And taking the time to look at the technology available to you. You don't have to be a computer engineer to understand some of the generalities in a modeling technique. You can just talk to the software vendor, and most of the time the support team or the programmers there can help you have a better understanding of when that tool is best applied. So I can control technology and mindset, and culture I can influence by having a good mindset and utilizing technology. And so that will slowly shift culture. And I think that's really where that question stems from, is it's good to have all three for sure. And that's typically how you can get there.
Awesome. And then I've got another question here for you as well, Des. Any recommendations or best practices for testing your model for a greenfield site? Additional drilling is an option, but can be expensive. So any other options?
Yeah, so this sounds super cheesy, but I think that if you can put together teams of people that you know have experience in that different deposit is great. So for example, most of us, when we've gone through school, we're used to having professors grade our work, right? And there are so many wonderful geologists out there that you can connect to through LinkedIn who I've sent models to. Like I have some friends who work at SRK and Golder, and I'm like, hey, I put this together. The client gave me permission to share this with you. What do you think about this? Because I agree, greenfields is really difficult, and utilizing deposit analogs that are out there from other known deposits or deposits that have been mined are extremely useful in helping us get to that proper geologic thought. And then doing peer review with others who have experience in similar deposit types will give you that ability to test your hypotheses.
Awesome. Well, thank you, Des. So in the interest of time, I think we're going to wrap this up. Don't worry if your question was not answered. We will definitely reach out to you and get that answered. If you've got additional questions, feel free to reach out to Desiree or email us directly at support@maptek.com. So then on behalf of the entire Maptek team, thank you very much for attending and have a fantastic day.